Hi. So we're moving on here, talking about chemical equilibrium. And we've introduced the quotient. Let me get my microphone range there. We've introduced the quotient, right? Do you remember what the quotient is?
For this reaction?
Yeah, you can tell me the quotient for this reaction, for this question right here, this reaction. What's the quotient?
The concentration of hydrogen ion to the cubed, the concentration of nitrogen gas, so 1 over the concentration of ammonia squared.
Very good. That is the quotient for the equilibrium. Its value would be Q. Once it reaches equilibrium, we actually know that, well, not for this one here. This is the quotient for this one. But for the quotient for this reaction, we're told that once the quotient reaches equilibrium, it will equal 500. And the question is, what would be the K for this reaction here? If this one equals 500, what's the K for this reaction?
Well, let's see. We just wrote the quotient for the bottom one. Let's write the quotient for the top one.
All right, the quotient for the top one is what?
NH3 squared. I guess it's just going to be the same thing, but the inverse, right?
That's right. So it's just what we wrote, but it's the inverse now, right? And if we're told that K will equal 500, the quotient will equal 500 when it's at equilibrium, and that's what K is, it's the quotient at equilibrium, then when this reaches equilibrium, it'll be what?
1 over 500?
Very good, 1 over 500. Excellent job. Okay, what about this one? Do we know anything about this reaction here?
Well, let's see. How does that reaction there is the top reaction divided by 2, is that right?
That's right. It's the top reaction divided by 2. So how does the quotient change? This 500. Do I divide it by 2 as well?
I can't remember. How do you do that?
Well, let's go back and choose a simple scenario and just think about it. A in equilibrium with B, all right? And then 2A in equilibrium with 2B, okay? The quotient for this?
B over A.
The quotient for this one here?
2B over 2A?
No, not 2B over 2A.
Oh, B squared over A squared.
Very good. B squared over A squared. So how do they relate?
Does B squared over A squared equal B over A squared?
It does. So we talked about that math before, but these two are equal to each other. Therefore, if you multiply by 2, you square the K value. If you have this value and you're looking for that one, you have to take the square root of it.
Oh, so it's the square root of 500?
That's right, the square root of 500. Excellent job. Okay, so let's talk about then what a large K value means, what a small K value means, and what a K value that's close to 1 would mean. What do you think? What would a large K value indicate?
Well, you said that large K's meant that at equilibrium there's more product?
That's right. That's right. It's very good. Let's, again, go back to a simple reaction, A and B. The quotient would be concentration of B over concentration of A. At equilibrium, if I know that at equilibrium this value is 1,000, then that means at equilibrium the concentration of B is going to be much higher than the concentration of A. So products predominate when this K is large. When K is very small, reactants predominate, right?
Yeah, okay.
Very good. Here's a reaction. If we know that the K value is 0.48 at 25 degrees Celsius, does the reaction favor products or reactants at this temperature?
0.48? Well, that's small, so it's going to favor let's see, if it was large, then that would mean products would be a higher concentration. So small means it favors reactants.
That's right, it favors reactants. Now, it's not very far from 1. It's kind of close to 1. What did we say at 1?
Oh, at 1, then a reasonable amounts of products and reactants were around.
That's right. So, we kind of have to see here that we're at 0.48, so we're going to have a reasonable amount of both, even though reactants are going to be predominant. Okay. Which is the most efficient reaction? Which of these K values would indicate the most efficient reaction? Now, what does efficient mean?
I don't know.
Well, efficient is how the reaction proceeds towards products as it's written. So if A is the reactant and B is the product as it's written here, then A, producing the product, would be effective. That reaction would be effective, so efficient, right? So a large K value would mean more products, therefore the larger K value here is going to be the more efficient reaction. What's our largest K value?
C, minus 10.
Well, these are minus values, right? So.
Oh, yeah. So, let's see, A or D. D would be the most efficient reaction.
Very good, because that is our largest K value on that list there. All right. So, the relationships between Q and K. K is what the quotient will be when it reaches equilibrium. Q is what the quotient is at any given moment in time that somebody might tell you the quotient for a reaction. So, Le Chatelier's principle, a principle which says that when there is more reactant than there are products, that speeds up the reaction of the reactants to go towards product. On the other hand, if there's more product than there is reactant, that will speed up the reaction to go towards reactants, right? So Le Chatelier's principle will cause shifts to occur until Q will become equal to K. All right? So, concentration affects the value of Q and helps predict the reaction progress. So if we know that, for example, here's my reaction, here's my Q for my reaction, meaning that my K for my reaction, meaning that at equilibrium, we'll get a lot of B, and I start off with 1 molar of A and nothing else, then I know that this reaction is going to proceed to the right until the concentration of B is significantly more than that of A. All right. These are the temperature effects on the value of K. If a process is endothermic, then the reaction will increase. Endothermic reactions increase K with increasing temperatures. If it's exothermic, on the other hand, reactions will decrease K with increasing temperatures. Now, let's draw that out so we get a little bit of an understanding of what this means. Let's have a little bit more complex reaction, A plus B going to C plus D, and let's say this is an exothermic reaction. If this is an exothermic reaction, then that means that heat is what? Released or required?
Did you say endothermic or exothermic?
Exothermic.
Well, that means heat is released.
Okay, and if heat is released, I can write heat as a product. All right? And if heat is a product, and I add more heat to this reaction, then it's like I'm putting more material on this side. And if there's more material than there is over here, the reaction is going to proceed to the left, or increasing the temperature is going to shift the equilibrium towards the reactant side. Now, just like if I have this reaction as it's written, and this time I'm not going to change the heat, I'm just going to add more of a given chemical. Let's say I increase the amount of A and B in my reaction. Well, if I put more A and B in, more A and B is going to be able to find each other and form more C and D. And so the equilibrium will shift to the right. Additionally, another thing I can do is to remove material. So for example, if I remove C and D, I remove it, take it out. Well, then C and D can't react to form A and B, and so more A and B will react and produce more C and D. So the equilibrium, we say again, shifts to the right. All right, so you can think of it in terms of a relationship between Q and K. I think it's easier just to think about Le Chatelier's principle, and this is what Le Chatelier's principle is, that when you perturb an equilibrium, the equilibrium will adjust to fill in any perturbation that you made, or to remove any excess that you've added. So let's go through some examples. Here's a chemical reaction. What's expected if I add more NH3?
In that reaction there?
Yeah, so this reaction is occurring. It's at equilibrium, apparently, right? If I add more ammonia, what's going to happen?
If there's more ammonia, then more of it will be able to react with the reactant, and the reaction will shift to the right?
That's right. The reaction will shift to the right because we've added more material here, and it goes to the right. Another way you can think about it is, before we added the ammonia, if this is at equilibrium, then Q equals K. If I add more if I add more reactant, then that goes on the bottom of the quotient, and the Q value decreases. And to help the Q value go back up to the K, we're going to need to produce more product. So same thing, the equilibrium will shift to the right. All right? How about if copper ion is added, and the copper ion contributes to the formation of this material here?
So if you add copper ion, you add that's going to shift to the right too.
That's right. It's going to also shift to the right, because upon adding this, the denominator in our quotient will be larger, Q will become smaller than K, and the shift to the right will help adjust for that. Okay, what will happen if we increase the pressure on this system here? In this kind of a situation, we have N2, H2, and NH3, right? And let's say this is all occurring in some sort of a vessel here. But we have a piston on the vessel that can push down when we want to, and it decreases the volume, which will increase the pressure of the whole system. All right? How will increasing the pressure change this reaction, or will it?
Well, it's going to change the concentration of everything, though, right? Because it's all gases.
That's right. So the concentration of nitrogen gas will increase, the concentration of hydrogen gas will increase, and the concentration of ammonia will increase. But which of these reactions, the one going to the right or the one going to the left, is dependent on molecules finding each other?
What do you mean?
Well, for ammonia to decompose this way, does it need to find another ammonia molecule?
I'm not sure.
Well, we don't know for sure, but there's only one entity here. Now, it does have a 2 in front of it, but that doesn't necessarily indicate the order of the reaction, right? However, going from here to the right, there are 4 molecules that end up combining together somewhere. And so maybe there's 2, maybe it's just 1 over here going to the left, but here we have 4, at least 2, and possibly up to 4 that are shifting, or that are required to come together to go to the right. And so when we increase the pressure, it makes it easier for these to find each other and produce this. Additionally, in the end, this side of the equation only has 2 moles of gas, whereas this side over here has 4 moles of gas. And when there's a higher pressure, we're going to want to take up less volume. And so this side will be favorable. So what will happen if the pressure is increased? The reaction will shift to the right because, like we said, for the reasons that we explained. Okay. How about this? What happens if we remove PO4 3 minus?
Well, that's a product. If you remove it, then the reaction is going to shift to the right to try to fill it up again.
That's right. We remove this, and now there's nothing to come back this way. Therefore, more of this will react and go that way until K is again reached. All right. Good job.